And now I'm putting audio into the YouTube as well. One moment, let me move that. All right, so now this room is simultaneously streaming onto both Zoom and onto YouTube. Just a second. Perfect. Okay, great. So now both are actually running. I apologize that the Zoom room wasn't big enough, but I guess we have learned for next time, we need to have more people. If you're actually in the Zoom room, I encourage you to stay here. The Zoom room has a very slight advantage that there is not a 2-second delay. On the main thing, on the YouTube thing, there's a slight 2-second delay. And what we'll do next time is we'll make sure that the Zoom room is big enough to fit everybody. Okay, right. Oh, interesting. So this is actually an interesting comment. So it looks like people are comparing the two different things. If you are watching it on the YouTube, you will probably notice that the video quality is more clear, except that the participation has a 2 to 10 second lag, and also anything that I say has about a 2 to 10 second lag. On the other hand, if you happen to be on the Zoom, the Zoom happens to be with no lag. On the other hand, it's a little bit more fuzzy. So I guess you can choose whichever one you prefer. And I think that's also showing something about the way math works. Somehow you can't always have both, and that's because of the problem of the internet speed. And so what YouTube does is it maximizes the quality of the video at a cost of delaying it by about 2 seconds. Okay, now where did my pen go? Just a second. I think when I answered the phone call, I put my pen onto the other table. One moment. Now you're watching what happens. Yeah, there it is. It was on the computer the entire time. Okay, great. So let's continue on. So we were just in the middle of talking about question number 9. And when we were talking about question number 9, it turned out we shouldn't minus 1, we should minus 2. So question number 9 is a relatively fast question. It's just, instead of the 3, 5, and 7, you subtract 1 from 2 from each of the dimensions, 1 from each side. And what you get is you get 1 times 3 times 5, which is 15. So the answer to question number 9 is 15. Let's continue. Okay. Yes, I see some people are commenting about the math of the Zoom and of the YouTube. I guess some people are curious if they can compare the two different qualities. You're welcome to. But I would actually not be surprised if there are just people who choose one instead of the other, whichever one you prefer. Let's do some more questions. Okay, here's a geometry question. Let's try this geometry question. This happens to be in the junior round, question number 12. So question number 12 is talking about a right pyramid. So here we have a right pyramid, and it has a rectangular base measuring 12 by 16 inches. The distance between the apex of the pyramid and each of the 4 vertices of the rectangular base is 26 inches. What's the volume of the pyramid in cubic inches? When I look at a question like this, I always think, well, they didn't ask me to say anything about simplest radical form, so that means that things are probably not going to have square roots. And then I'm also going to have to use some kind of hypotenuses of right triangles. So I see this 26, and something about the 26 makes me think of a very particular right triangle. Do you think of any right triangle if you want to have nice whole numbers? If you have a 26? Yes, the 5, 12, 13 right triangle, right? So there is a right triangle which is 5, 12, 13. And so here's where you cross your fingers and you say, I really, really hope that there's going to be a right triangle which is a 5, 12, 13 just blown up by a factor of 2. Now, if that's the case, this is what happens when I take the lines from the apex of the pyramid down to the corners. So if I'm going down to the corners, and I'm going down at 26, let me draw a picture now. Let's draw a picture. So we have the four corners, the base of the pyramid. I guess I can write that. Base of the pyramid. And we have this, right? And each of those is 26. So each of those is 2 times 13. Then I really hope there's a 5, 12, 13 going on here. Well, I better draw the altitude, which goes all the way to the center, right? Going all the way to the center. And I would like to have that there's a 5, 12, 13. What do you think? Well, the base happened to be 12 and 16. So if the base happened to be 12 and 16, like this, the other thing is I'm thinking, am I going to get a 5 or am I going to get a 12 out of this thing, this diagonal over here? Something that makes me happy is that 5. I actually know another right triangle which has 5 as its long side, as its hypotenuse. I know a 3, 4, 5. Yes. And if I look at this, I see a 12 and a 16. I'm also happy because the 12 and 16 is like a 3, 4, 5, right? In fact, a 12 and a 16 would give me a 3, 4, 5, where I've multiplied the 3, 4, 5 by how much? This is not drawn to scale, but it's 3, 4, 5 times 4, right? Times 4. So if that's the case, then the height, then the hypotenuse happens to be this 20. Now I'm really happy, because if I've got 20 going across here, right? So that's 20 going across here. That means that the yellow, how long is the yellow? If the whole thing is 20, then the yellow is 10. This is great. So I've got my 10. And now I see my entire 5, 12, 13 has arrived. So I've got my 5, 12, 13 going from this 5. This has to be the 12 times 2, and that's the 13 times 2, which is the 26. So this is 12 times 2, which is 24. At this point, I have everything I need in order to go and find the volume, because the volume is 1/3 times the base times the height. So let's finish. The volume is equal to 1/3 times the base area, 12 times 16, times the height of 24. What's the most efficient way to multiply these numbers? I guess we have to clean up the 1/3 and the 12, right? So if you do that, you get 4. And now I have to multiply these numbers. Does anyone have any good ways of multiplying these numbers? Actually, let's do a challenge. I wonder if I can multiply this in my head. I'll tell you how. It's because I know that there's a 4 times a 24. That's 96. That's 100 minus 4. Okay? So I'm doing some stuff in my head. 4 times 24 is 96. That's 100 minus 4. Now, 100 is easy to multiply by 16. That's 1600. And I have to minus 4 times 16. But 4 times 16 is 64. 1600 minus 64, 1536. Is that right? Now let's double check. So I always like to run these, challenge myself a little bit. So over here, if I want to check it a different way, let's check it a different way. I'll write it the same way, just so that you know what I did. I did it as 16 times 96, which is 100 minus 4. And that is equal to 1600 minus 64. And that happens to be 1536. So that's my answer to this question. Is this right? Let's find out. I can ask my moderators, but at the same time, we also have the crowds. We have the crowds on both YouTube and on Zoom at the same time. So looks like we're good. I think that's the answer. 1536. I like this question because, to be honest, I didn't actually solve the question before I looked at it, before I just did it. This is the first time I've solved the question. However, when I saw the numbers, I saw 26, 12, and 16. And in my head, what I saw was 26 is going to give me like this 5, 12, 13 thing. And the 12 and the 16 are going to give me the 5 because it's a 3, 4, 5. So I knew that the answer would be nice. Okay, let's keep going. So these are all questions. We were just doing some questions which are from the junior division. Now let's move to something else. What else do we have here? Other questions that we can talk about. I want to talk about something from the senior division. So the senior division, they had a bunch of different contest problems here. And so I'll put this aside. We have a lot of questions that we could have chosen from. But for the senior division, where's one that I chose? Oh, right. Okay, so here's another question. And I want to emphasize, I was trying to do some questions that are more approachable and some questions that are harder, because as we do all of these different ones, then hopefully you, no matter where you are in your experience, you can pick up something. So I want to talk about a question from the senior division now. So let me unfold my computer. Go here. Close this. Senior individual. Here we go. Let's zoom in. Okay. And I want to start with question number, let's do 18. Well, no, let's do this one. Let's do 13. 13 was also neat. How many rectangles with sides on the grid lines have even area in a 6x6 grid of unit squares? So now this happens to be a harder question. Oh, I will also do the guts problems. If somebody was asking, there are some really interesting questions in the guts round. So I'm going to think about this one. How many rectangles with sides on the grid lines have even area? And I have to draw a 6x6 grid of unit squares. Okay, let's try to draw a 6x6 grid. I have to fold my computer up again. Okay. 6x6 grid, huh? At least it wasn't a 60x60 grid. I can still draw a 6x6 grid without taking the entire hour. So here's a 6x6 grid. And inside this 6x6 grid, the question is going to be, how many rectangles of even area can I make? So I like this one because I think it's a challenge. And I also think I have an idea that might be useful. So which do you think is easier, by the way? To find the number of rectangles with even area or the number of rectangles with odd area? Odd area is actually easier. The only way to get odd area is to make sure that both the length and the width happen to be odd. Okay, so what I'm actually going to do is I'm going to say that the number of rectangles with even area is equal to the number of rectangles with odd area. No, it's not. It's the number of rectangles at all. Okay, number of rectangles altogether minus the number of rectangles with odd area. Now there's a reason I'm doing this. It's because it turns out there's a particularly easy way to find out the number of rectangles. The number of rectangles, all you have to do is just count them all, right? Let's count them all. 1, 2, 3, 4. No. Let's not do that. Counting them all is a bad idea. Instead, we could do multiplication. So there's a wonderful, wonderful counting trick here, which we actually talked about, I think, in one of my classes. But if you want to make a rectangle, you know how you make one? You take two horizontal lines. That's a very weird horizontal line. Oh, I can use a highlighter. 1 second. You use two horizontal lines and two vertical lines. Any choice of two horizontal lines and two vertical lines is going to give you a rectangle. So I can get this first thing like bam, like that. This is in the senior division, so I guess the question is supposed to be a little bit harder, but that's an amazing trick. Okay, to be able to count all of the rectangles in this picture by just saying, find all ways to pick two horizontal and two vertical lines, boom, you're done. Okay, what's this? How many ways are there to pick two horizontal lines? Well, the number of ways to pick two horizontal, whoa, I don't want my highlighter for this. The number of ways to pick two horizontal lines is what's called 7 choose 2. Because there are 7 horizontal lines, and I want to choose 2 of them. And I need to choose 2 vertical lines as well. And so there's times another 7 choose 2. Before I evaluate that, let's see how we can figure this out. If I want to know how many rectangles there are with odd area, how do you do that? Well, if you look at what's going on, if I want to get an odd area, I need to have that both of these both the gap between horizontal lines and the gap between vertical lines has to be odd. And for me, that seems to give me an idea of what's called parity. Let me draw another picture, another diagram, just so I can stare at it. So here's another diagram. Oh, I actually want to, I want to do some color switching, okay? I want to do something crazy. I'm going to draw the vertical lines alternating in color. Yellow, pink, yellow, pink, yellow, pink. I'm supposed to have 7 of these. So far, how many do I have? I have 6 of them. Here's the 7th. Okay? Those are my 7 vertical lines, just like those 7 vertical lines. I'm also going to draw the 7 horizontal lines, but alternating in color. Blue, white. Oh, wait. I want it to all balance. Okay, so if I want it to all balance, I believe the middle one is going to be white. Hope this works. The blue is the last. And so, yeah, this works. So there should be a blue here, and 2 whites here. That was not bisected. Let's do this. How many people are sort of understanding what I've just done here? So I've just gone, I see. Somebody says they see where I'm going. All right. So I've just drawn the same picture here, just with some colors. All right. I'm just being silly. I just drew some alternating colors. But why? The reason why is because if I want to go and pick 2 horizontal lines for which the gap between them is an odd distance, you know what I have to do? Suppose I'm looking at the horizontal lines. Can I pick 2 blues? No, I can't pick 2 blues, because if I pick 2 blues, the gap between them is even. And so I need to pick 1 blue and 1 white. And how about the vertical stuff, right? For the vertical stuff here, if I'm going to make sure that I pick a rectangle, I want these 2 walls of the rectangle to have that the gap between the walls is even, I have to pick 1 pink and 1 yellow. I cannot pick both pink. I cannot pick both yellow. So this tricky idea here for the second piece is the way to pick a rectangle, the ways to get a rectangle with odd area is that you must pick 1 of the blue horizontals, 1 of the white horizontals, 1 of the yellow verticals, and 1 of the pink verticals. In that case, what do I multiply? Can someone tell me what this should be? Aha. Yes. What you should say is that, look, if I want to pick the blues, there are 4 choices for the blues. I'll even use the colors here, right? There are 4 choices for the blues. How many choices for the whites? 3. That's how I make my horizontal. For my verticals, I have 4 choices for the yellows, and I have 3 choices for the pinks. So that's the number of ways I can pick a rectangle with odd area. Do I have any colors left? Oh, I have a green. Good. I'll put an arrow there, and I'll write minus, and I'll write an equal sign. We're just like making completely random colors here. All right, I just have to multiply, then I'm done. What's 7 choose 2? 7 choose 2. Okay, so 7 choose 2 is like 7 ways to pick the first one times 6 ways to pick the second one, divided by 2 ways that I could have, I could have counted the same thing twice. And then I times 7 ways times 6 ways over 2. And then minus 4 times 3 times 4 times 3. Is everyone still with me? All I had to do here is I had to say, how can I pick 2 of those 7 lines? So yeah, you just, 7 ways to pick 1 of them, 6 ways to pick one that is not yet picked, and then divide by 2 because you've got to flip. Okay. So in that case, I just need to subtract. Now, you could say it's just like 21 times 21 minus this. You could. Another way is maybe we can factor some stuff out, because I see that I have a 2 and 6 are going to cancel and give me a 3. This is going to give me a 3. There are also 2 factors of 3 there. I'll do it that way. So if I pull out the factors of 3, that's a 9. And what I have here is 49 minus 16. It's unclear to me this was any better. But what I've just done is I've said, look, there's a 3 and there's a 3. I'll accumulate them into a 9. And what's left is a 7 times 7, 49 times a 9. And over here I have a 3 times a 3, and that gives me a 16 times a 9. So now I have to subtract. 49 minus 16. What is this? Oh, this is easy. I don't have to borrow because it's a 9 at the end. So what is this? Like 33 times 9? Hopefully. 33 times 9? How do you multiply a number by 9? Well, you multiply it by 10, and then you subtract it. So what's 330 minus 33? 330 minus 30 is 300, minus 3 is 297. So the answer to this whole thing is 330 minus 33, 297. So that's my proposed answer for this question. Is it right? I'm not sure. I mean, when I say I'm not sure, I don't have any moderators with me, it seems. So I guess what I will do is I happen to have the answer key, but it looks like a lot of people here seem to think it looks right. So I think that's right. And I see that some people say, you know, they might have skipped some of the questions, some of the other questions because they didn't feel as comfortable with other things. Thank you very much for confirming that this is right. But this is a combinatorics question where if you try to do it with the brute force method of just counting all of the rectangles with even area, ouch, it could take a while. But instead what we did here is we went and just did subtraction, and we were able to use straight up multiplication to do each of those things. All right, we still have some time. We still have a bunch of time. Let's do some more questions. The next one I wanted to do was this question number 18. Let's look at it. Time for some geometry. I guess we already did some geometry, but let's keep going. So I want to talk about question number 18. So here we're scrolling. By the way, if you're curious where these questions are from, this is the Cowconuts math competition, which just finished. So we have question number 18, stop. So we have some square. ABCD is a square, and P is a point inside the square, such that the distances from P to sides AB and AD are 3 and 4, respectively, and PC equals 5. Find the area of ABCD. I like these questions because they feel sort of like puzzles. And when it's a puzzle, I don't really know what I need to do to solve it. So I know I'll start by drawing a picture. And the picture is going to have some distances from a point in the middle to the sides. Oh, sides. Ha! Actually, when I read it completely differently. Okay, maybe this is actually going to be easier than I thought. Oh, I thought it was to the corners. I read the question wrong. Well, let's do the question anyway. So we have this square, we have a point, and the distances from it to the sides AB and AD. Ooh, it's going to be important that the letters are in order, okay? So I'm going to flip between, some drawings. I'm going to flip between a drawing and also looking back at the problem statement, okay? So it's drawing time. So I need to make my square ABCD. So let's go with A, B, C, and D. Mathematicians like to label things where it goes counterclockwise. I don't know why. Somehow we think that angles are better measured counterclockwise. So now we have a point, right? So there's a point inside such that the distance from P to side AB is 3 and P to side AD is 4. So it's closer to AB than it is to AD. So it's like 3 and 4, something like this. AB, oops, I wanted to change colors. And I'll redraw this in a second as soon as I figure out what the relative lengths are. That's like a 3, that's like a 4, okay? And over there, PC is, oh, I see. So the distance from P to point C is 5. That means that this diagram is totally nuts. That means I'm going to erase it and draw it to scale, okay? So let me go and now properly draw this. We want to go and find the area of the entire square. So as you can see, this is bogus. How can that be 6? How can that be 5? So let's go and fix it. So look, it's 3. That didn't look like 3. It's probably like this. Three, 4, and 5. Something like this. Oh, nifty. Actually, as I look at this, I'm starting to notice something interesting. First of all, 3 and 4. Does 3, 4, 5 make you think of anything? 3, 4, 5 is a right triangle. That means that if I drew this, you know what that is? This is another 3, right? So that's a 5. Now I know how I can draw this picture. I can draw this picture more beautifully by using the fact that this point P needs to be the same distance from A as it is from C. Does that tell you anything about where the point P is located? If this point P is supposed to be the same distance from A as from C, where should it be? Should it be in the middle? Well, not necessarily. It's not necessarily in the middle, but it's on the diagonal. It's on this BD, because this BD is a line of symmetry for the entire square, right? So every point on BD has the same distance from both of those two other points, A and C. Another way of saying that is that the perpendicular bisector of AC is actually this diagonal. And whenever I have a point which is equal distance from 2 points, it's on that perpendicular bisector. Okay, so let's redraw again. And this time we'll redraw again using the fact that I know that the point P is going to be somewhere on this line. The point P is somewhere on this line. Does it mean that the point P is right in the middle? Maybe it does. Look, maybe the point P is right here, right? Maybe that's my point. And look, that's 5. And this is 3. And this is 4. How many people like this? You think this is right? No, this can't be right. The reason this can't be right is because look, I mean, come on, there's no way. Because this is supposed to be the same as that. It's the center of the square, right? If it's the center of the square, no way. Somebody else said, probably not, would be too easy. That's another way of thinking about this, because this question is what? This is question number 18, right? So it should be hard. So, no, it can't be. But look at it. This is supposed to be same as that. But this is already making me think that I think I can see a way to get this answer really nicely. Okay? So it's not going to be there. Where is it then? I don't know. Somewhere. Like here. Oh, you know what? I can sort of draw it to scale. I bet it's like this. This looks like it would be a 3 and a 4. Now, there's a very interesting thing. The question asked, what's the area of the square? So if I want to know the area of the square, all I need is a side length, right? Yes, I could just do it algebraically, says somebody, but there's a much better way. The much better way is, did you see how this became a 3 and a 4? Actually, in general, whenever I have a right triangle, here's a right triangle, I hope. 45, 90 right triangle. A right triangle where this is equal to that. Do you know how this purple path length compares to this yellow path length? How do those two lengths compare? Where I'm going like boink and boink. They're equal. Yes, they're the same. And the reason they're the same, actually, is because, you know, this is the y equals x line. And so, well, here's another way to see that they're the same. It's very easy. See this thing? This is the same length as up there, right? And this is the same length as over there. Does that make sense to people? See this guy? This is the same length as that. Of course, it just kind of goes up. And this one, why is this one the same length as this one? Well, it's because I'm just going up, right? It's basically what's called, it's another 45, 90 right triangle. Basically, this whole picture is just like 45, 90 right triangles. Therefore, the yellow plus this yellow is just equal to the blue. Aha. That means that if I want to know how long the blue is, I just need to know how long this bouncy line is. Okay? Well then, here's a bouncy line. 4 plus 3. Boom! 7. That means that this is 7. And this is 7. And so the answer is just going to be that the area of the whole square is just 7 times 7, which is 49. Boom! We're done. That was it. We don't need any trigonometry. Somebody in the YouTube has commented, do we use trigonometry? No need, no need. We don't need any algebra. We don't need any crazy things. It's just Boom! The main insight, you see, was just saying, why did the question authors give us a 3, a 4, and a 5? Can we find something clever about the 3 and the 4 and the 5? Usually the question author won't give you 3 totally useless numbers. So when you see the 3, 4, 5, the first observation was, ooh, that is the same as that. And that's how we knew that this point P was on that diagonal. Once you knew it was on the diagonal, you're done because of this bouncy property. Okay? That's it. So the answer is 49. Area of ABCD is equal to 49. I hope that's the right answer. Again, my moderation team is not here today, so I hope that's the right answer. But I think enough people here have seen it, have watched what I did, that I think people are happy. And indeed, we're going to call this the BOINC property from now on. BOINC it is. Let's do some more problems. What else do we have here? We've got some time. Good. I want to make sure we do some of these other questions which are really nifty. So I want to get to the guts round. There was a guts problem in the junior division that was pretty. There were 2 of them I wanted to hit. We will have time. So I want to do 2 more questions. So just so you know, this session was actually only supposed to be for 1 hour, which is not enough time to do justice to all of the problems here. And so since we had both junior and senior divisions, I chose to grab the pretty interesting questions from the junior division, plus a few from the senior division, with the idea that even if you're older, at least the next questions I'm going to pull from the junior are, pretty interesting, and you'll get something from them anyway. All right. Now, oh no, somebody's going to add a Wikipedia article to BOINC property. All right, let's go and do junior guts. There was some question here I really liked. Well, there's a whole bunch I really liked. Let's zoom in some more. And I want to start with question number 3. This is from their round, which is called the guts round. And so here comes question number 3. And it says, suppose I have a positive real number x, such that x squared plus 1 over x squared equals 23. What is the value of x to the power 5 plus 1 over x to the power 5? Well, clearly, all you have to do is just solve for x, right? There's a nice equation, x squared plus 1 over x squared equals 23. It's a quadratic. It only has things in x squared. So we should just remember the quadratic formula and put it in. Well, sort of. And in fact, it's not really a quadratic. It's actually a quartic, which is not fun. But you could actually solve for this using the quadratic equation. If you said, let's let x squared be a new number called y, you could do that. However, there's a much better way. And the much better way is to say, look at that pattern. X squared plus 1 over x squared. And I need to see something about x to the 5th plus 1 over x to the 5th. I wonder if I could figure out what x plus 1 over x is. If I could figure that out, maybe that's the beginning of a pattern. Okay? So let me rewrite the question. We have x squared plus 1 over x squared equals 23. So we have x squared plus 1 over x squared equals 23. Suppose the first goal is to figure out what x plus 1 over x is. I wonder if I could figure that out. Well, obviously, x plus 1 over x is just the square root of 23. Who likes this? Who agrees with me? Is it just the square root of 23? If x squared plus 1 over x squared is 23, then x plus 1 over x is the square root of 23, right? No, it's because if you actually tried to square this, you get some middle terms, right? This is x plus 1 over x multiplied by x plus 1 over x. And that's that is x squared plus, now when I take the cross terms, I have an x times a 1 over x. Oh, that's 1. I like that. And then plus a 1 over x times an x. Another one. Neat. Plus 2. Plus 1 over x squared. Okay. Do we like this? Actually, we like this a lot. Because look at that. Do you know anything about what this might be equal to? 23 plus 2. 25. And I like that it's a perfect square. No square roots are going to appear. So that means that x plus 1 over x squared is 25. Now I have something. X plus 1 over x is equal to plus or minus 25? No, plus or minus 5. But is it plus or is it minus? Here's where we need to remember. The question told us, actually, that x is a positive real number. So the questioner already told us x is positive. And if x is supposed to be positive, then there's no way you could have x plus 1 over x to be minus 5, right? There's no way. So it has to be plus 5. Not minus 5, since x is positive. Okay, so now x plus 1 over x is just 5. In that case, now I can actually try to solve the problem. The problem asked us to figure out what is x to the 5th plus 1 over x to the 5th. So clearly all I have to do is just figure out what is x plus 1 over x raised to the power 5. Right? Now, it turns out that this, whenever you expand this, there's a nice bunch of coefficients that pop out. These are the coefficients from Pascal's triangle. I'm going to run to another screen where I expand that out a little bit, and then we'll just use the same numbers. So if I ever want to do something like a plus b, where a is something and b is something, if I want to raise it to the first power, it's really boring. It's 1a plus 1b. But I'm writing the ones on purpose. Okay? And the reason is because I want to look at what these coefficients are. Coefficient is whatever number is in front. What happens when I do a plus b squared? We just saw we got 1a squared plus twice ab plus 1b squared. Now what happens if I do cubed? If I want to know a plus b whole thing cubed, you see I can do it by taking the 1a squared plus the 2ab plus the 1b squared and multiplying it by a plus b. If I want to do this, now I'm going to start combining some terms together. I'll take the a and join it with each of those three things. Let's use some colors. I'll use yellow for those, and I'll use blue for those. Okay, so that's equal to the ones, not yellow, green. I'll use green for those. And now, if I put them together, I have how much a cubed? I have 1a cubed plus 2a squared b's plus 1ab squareds. And the b thing gives me plus, I'm gonna switch it over, I'll shift it over a little bit, plus 1a squared b plus 2ab squared plus 1b cubed. I want to emphasize how this came about. This b joined with the 1a squared gave me the 1a squared b. The b joined with the 2ab gave me 2ab squared. The b joined with the 1b squared gave me the 1b cubed. But now, when I do this, I can add them. You see, I collected it so that the like terms are right above each other. And you see what's happening. I'm actually going to take 2 plus 1 and 1 plus 2. What's really happening is I'm going to take whatever were the previous coefficients and I add the ones that were next to each other together. And so that gives me 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. Is this okay? So if I have here, I'm like, I had a 1, 1, then I had a 1, 2, 1. Let's draw a pattern. I had a 1, 1, and I had a 1, 2, 1, and now I have a 1, 3, 3, 1. Has anyone ever seen this before? This is from the Pascal's triangle, right? And what's going on top? I guess I could even have said raised to the power 0 is just 1, right? I could even have stuck a 1 on top. But what you do is you're always going to add the two numbers above to get the number below. That's what's going on here. And the reason why you add the 2 above to get the 1 below is exactly what we just did. What we just did shows that when you multiply by a plus b, the a thing is here and the b thing is shifted over by 1. And because you shifted over by 1, that's exactly why you add together that one. Sorry, this one here is the same as that one, right? And since I shifted it over, then it joins with the 2. So I'm just explaining to you why this pattern works. Let's do it a few more times. If I want to know what is a plus b to the 5th, I just need to add 2 more rows. This is the row for cubed. Let's add a row for 4th, and let's add a row for 5th. For the 4th, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and here's a 1. And the last one is a 1. 1 plus 4 is 5. This is a 10. 6 plus 4 is also 10. 5 and a 1. Okay, so now I have a formula I can write down. So the formula is going to be 1a to the 5th plus 5a to the 4th b's plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the 4th plus 1b to the 5th, just in time before running into me. So that's what happens if I take a 5th power. Now we flip back to the problem we were just doing. Now we know the coefficients are 1, 5, 10, 10, 5, 1. Let's pull back. And you're right, this is called the binomial theorem. Somebody said in the Zoom chat, this is the binomial theorem. Okay, so now let's pull back. 1, 5, 10, 10, 5, 1. And how did we do this? The way we did this is we just used the same principle we just saw, which is that you're going to shift over by 1 and then add, which is why you always add the two things next to each other to get the one below. Okay, so 1, 5, 10, 10, 5, 1, right? So what's the first one? Well, now a is x and b is 1 over x. So let me write it out slowly. I have a 1 x to the 5 plus 5 x to the power 4 1 over x plus 10 x cubed 1 over x squared plus 10 x squared 1 over x cubed plus 5 running into my head x 1 over x to the 4 and plus 1 over x to the power 5. I have to duck. So if I look at this, I'm like, that's what I have. And I know what it is. This thing here is just 5 to the power 5, whatever that is. We can figure that out later. This is 5 to the power 5. Okay, so apart from the thing that my head is blocking off, you see, that's what I wanted. I wanted to have this plus the thing over here. So that means that my answer, which is the x to the 5th plus the 1 over x to the 5th, my answer is just 5 to the 5th minus all this nonsense in the middle. What's the nonsense in the middle? So the answer is equal to the 5 to the 5th minus the nonsense in the middle. That is equal to, if I simplify, I have a 5x cubed plus 10x, because that x cubed times 1 over x squared is x to the 1, plus 10 times 1 over x plus, whoa, I need parentheses, plus 5 times 1 over x cubed. Okay. So now how do we do this? I know what I could figure out what 5 to the 5 is. But what about all this stuff? Well, I know some things. Look, do you know what is x plus 1 over x? Yes, I do. X plus 1 over x is 5, right? X plus 1 over x is 5. Let's now erase this minus sign. Not minus sign. Right? So the x plus 1 over x, that's going to be 5. It looks like all I need is I just need to know what is x cubed plus 1 over x cubed. But I can do that again. I can do the x cubed plus 1 over x cubed. Let's figure that one out. And once I figure that out, I'm done, right? Because I know what is x plus 1 over x. And I just need to know what's x cubed plus 1 over x cubed. How do you do that? We do the same thing again. If I want to know what's x cubed plus 1 over x cubed, I just cube the x plus 1 over x. And remember, the pattern is 1, 3, 3, 1 over here. So it's 1, I'll do it a bit faster, 1x cubed plus 3x plus 3 over x plus 1 over x cubed. Are people okay with this? This was just the 1, 3, 3, 1 pattern, okay? And so in that case, I know what this side is. That side is 5 cubed. That's 125. Okay? I also happen to know that x plus 1 over x was 5. So this is 15. Are people okay with this? So this was like 3 times 5, 15. So if I subtract 15, I get 110. That's equal to x cubed plus 1 over x cubed. Okay, now let's put everything together. All right, so now I have that the cube thing is 110. Let's go all the way back, all the way back. So I have 5 times that thing, 5 times 110. Let's look at this bracket here. This is 5 times 110 plus 10 times 5. Those aren't decimal points, those are multiply signs. I just didn't write x's for times because that looks like x, right? Oh, somebody has a question. How is that thing 15? Does that mean that I did it wrong? Let's go and take a look. It's entirely possible that I do arithmetic wrong. How is this 15? This is because it's 3 times x plus 1 over x. I think it's 15 because x plus 1 over x is 5. We figured that out already. Okay, so now I'm back here. And I'm like, that's my answer. It's 5 to the 5th minus this thing. Who wants to do that? Not really me, but I guess we have to. It's a math contest. So if I was going to tell you how I'm going to do this quickly, I'm going to factor out 25. The reason I'm going to factor out 25 is because this is a multiple of 25, and that's a multiple of 25. There's 2 5s in each. So if I factor out the 25, what do I get? I get 25 times 5 cubed, which is 125, minus, I now have to divide 110 by 5. Dividing by 5 is easy. You times 2 and you divide by 10. Or rather, I did it because I saw a 0 at the end. You divide by 10 and times 2. So it's 125 minus just plain 22, and then minus a 2. How many people are okay with this thing I just did here? What I've just done here is I've said this looks like huge numbers I don't want to mess with, so I'm going to simplify it a little bit. And so I will take 2 5s out, then I have 3 5s left, right? This is 3 5s, that's 2 5s. And if I take 2 5s out, take 1 out of here, and this one, there's 22 left, okay? So I have this 22. And if I take 2 5s out of this, there's a 2 left. And this is reasonable. What's 125 minus, oh my gosh, so nice? Wait a second, don't tell me the answer is this nice. I mean, 125 minus 24 is 101, right? This is 24. So it's 101 times 25. Does anyone know what's 25 times 101? I know what that is. 25, 25. Whenever you multiply by 101, multiplying a 2-digit number by 101, you just simply take the 2-digit number and take it again. And that's because when you multiply by 100, you shifted it over by 2 zeros, 2 spots. Okay, is that actually legitimately the answer? Now I'm really curious. It's just like too nice. Do I have anyone in this Zoom chat who actually is a person who organized the contest? I'm actually quite curious if that's the answer. I see a bunch of people saying yes, but I have no idea if they're trolling or if they actually know what the answer is. But I think what we'll say is it looks like it's pretty reasonable. It looks like people like 25, 25. Answer is correct. We're good. And so that finishes this question. This question was fun because it actually uses this thing called the binomial theorem. And with that, let me give you one last question. Okay, one last question which I noticed in the guts round. And even though this was a junior division, their guts round, even though this was a junior edition, their guts round had some pretty interesting stuff. I like this one. Question 23. I should accelerate this. We're going down to 23. There are a lot of words on these questions. Okay. So this is saying, find the number of fractions a over b in simplest form with 3/4 less than a over b less than 4/5, such that a plus b is less than 45. How do you do this kind of question? It's very short to state. Just find some fractions, which are between 3/4 and 4/5, so that the a plus b is less than 45. Okay, so here's what I'm going to do. I'm going to do something weird, all right? I want to find these fractions between 3/4 and 4/5. So let me see if something works. I'm not sure this will work. We'll find out soon. If it doesn't work, we have to do it the hard way. 3/4 and 4/5. I'm going to write down the fractions. The fractions. What do I mean by the fractions? Well, here's 0. It's just 0. And here's 1. Maybe I want more space. Lots more space. Okay, that's the first round. The second round, what I'm going to do is I'm going to take two fractions that are already here, and I'm going to add their numerators divided by adding their denominators. What does that mean? Adding their numerators is 0 plus 1, which is 1. Adding their denominators is 2. Now here's something really important. If I have two fractions which are in order, and if I add their numerators and add their denominators, that fraction is always in between them. Okay? So, right, and the reason why, I'll explain why if this actually is useful. Let's find out if this is useful. So I just did this. I want to do it again. So I just did this. I took the previous fractions, and in the middle, I put that. Now this is what it looks like, and I want to take all of the previous fractions and do that again. So if I do that again, add the numerators and add the denominators, 0 plus 1 is 1, 1 plus 2 is 3. So I got 1 over 3. Let me put it over here. 1 over 3. And the other one is 1 plus 1 is 2 over 2 plus 1 is 3. It's still in order. 0 over 1, 1 over 3, 1 over 2, 2 over 3, 1. Okay, done with that row. Let's do it again. Now I'm going to go through and systematically I'll put 4 more numbers in. So 0 plus 1 is 1. 1 plus 3 is 4. Isn't it cool that I don't ever have to simplify? I actually am not simplifying. I'm just writing them down, and they're already in simplest form. 1/4, 2 over 5. And over here, what's over here? So I have, this is 3 over 5. And over here is 3 over 4. Okay. And then let's do it again. So the next thing I do is I'll run it again. Okay, so let's run it again. And I get, over here is 0 plus 1 is 1, 1 plus 4 is 5. And notice I'm being careful. The yellow ones were all generated at the same time. So I'm generating the blue ones at the same time. And then I generated the yellow ones all in one go. Now I'm generating the green ones all in one go. This is 2 over 7. This is 3 over 8. I'm just adding fractions in the wrong way. I'm adding the tops and the bottoms. 3 over 7. Okay, I think. And then 1 plus 3 is 4 over 2 plus 5 is 7. 5 over 8. This is 5 over 7. And this is 4 over 5. Okay, that was kind of neat. What was the question again? Let's see. So I was supposed to find all of the fractions between 3/4 and 4/5. Where are those? Between here and here. I was supposed to find all of the fractions that are between those in simplest form with a plus b, where numerator and denominator add to less than 45. But do you see something neat that's going on? This is an amazing way of generating fractions. And in fact, this has a name. This is way more advanced than what I expect anyone to have learned in middle school or high school. I myself didn't hear about this until I became a Math Olympiad coach, and some students taught me about this. There's something called the fairy sequence. And the fairy sequence is telling you that you're able to generate all of the fractions in simplest form by doing what I just did here, where I just kind of run across, do a whole sweep, and when I'm done with the whole sweep, then I go and again, in the middle of everything, put the sum of the numerator and denominator. Numerators add over denominators add, and just put. And if you do that, and if you just keep doing it and doing it and doing it, you actually get every fraction exactly once. And also, you get them all in order. If you're curious about this at all, you can Google for fairy sequence afterwards. Prove it. This is more than we can do in this short period. I just wanted to end with this as a taste of somehow some interesting math. But now, suppose I knew that was true. Then how would I solve this problem? If I wanted to know how many of the fractions there are which are between these two, well, notice that every time you do this, you, number one, don't have to simplify. And number two, you get all the ones in between in the right order. So actually, the way you solve this problem, if you know about fairy sequences, is you say, Well, there's a 3/4 somewhere, and there's a 4/5 somewhere, and they just so happen to be consecutive after one round of generating this. So, in that case, now let's just do it again. So let's add 3 plus 4 over 4 plus 5. That is 7 over 9. And you should think of what I've just done here is I've just zoomed in. So here's the 3/4, here's the 4/5, and I've just zoomed in. Is this okay? So I'm saying that, between these two things, I've just zoomed in over here. So now let's continue. So if I do this, and this is, oh yeah, maybe here I want to explain something about why the number in the middle is always in the middle. You can think of this sort of as saying, imagine that you were playing basketball, and you got, in the first half, you tried 4 times and got 3 free throws. I mean, you got 3 baskets out of 4 attempts. So your average was 3/4. And in the second half of the game, you had 5 attempts, and you made 4 of them successfully. So if people looked at you in the first half, they would say your average was 3/4. If they looked at you in the second half, your average is 4/5. And what's your overall average? Well, obviously, how many did you try to shoot? 4 plus 5, which is the 9. How many did you make? 3 plus 4 is the 7. And of course, the average should be in between the two. So that's an easy way of knowing why if you add the numerator divided by add the denominator should be in between. So now let's keep going. So that would be the next thing. So what I'm saying is if I've zoomed in, forget about the rest of the sequence. Here are the numbers that I'm going to write in as my fractions. That goes there. What goes next? I do the summing again. 3 plus 7 is 10. 4 plus 9 is 13. 7 plus 4 is 11. 9 plus 5 is 14. Okay, that would be finishing another round. And let's finish another round. The next one after that would be 3 plus 10. You see, I'll go until this thing has the sum being 45 or bigger, because the question asked how many fractions are there where the sum of the numerator and denominator is at most 45. So okay, 3 plus 10 is 13. 4 plus 13 is 17. This is 10 plus 7 is 17. 13 plus 9 is 22. 7 plus 11 is 18. 9 plus 14 is 23. 11 plus 4 is 15. 14 plus 5 is 19. Okay, now what will happen if I keep going? I have to actually draw some arrows now, unfortunately. This thing will give me 13 plus 3 is 16. And 4 plus 17 is what, 21? 16 and 21 still add to less than 45, so it still counts. Okay, but now if I try to put something in between here, it's going to be bad, because I'm going to get 23 over 30. Adds up to too much. I have to stop at 45. The question said how many fractions where the numerator plus denominator is less than 45. So that's too big. Over here, I have a 27 over 30 something, too big. Over here, I have, what is this? So this is 24. If I wanted to use it, I would get 17 plus 7 is 24. Divided by 22 plus 9 is 31. Oh, that's too big. The sum, when I say too big, the sum is bigger than 45. Over here, I would have 7 plus 18 is 25 over 9 plus 23 is 32. Also too big. And if I look, all the rest of them are going to be too big, right? That's like in the 20s over the 20s. Yeah, that's too big. This is too big. How about this one? This one might be okay. This would give me, oh, my computer froze. 1 second. The way that I solved this, just a second, we might lose something that we wrote, but this is why I save everywhere. 1 moment. Yeah, so if this thing froze, what we do, we're back. Okay. Just a second. We'll finish up this question. Oh no, it looks like I didn't save at that point. Well, let's just do it real fast then. So that particular one, I usually press save as we keep going, but let's just quickly do this one again right where it was. So we had a 3/4, And now we know from the foresight of having done it, let's get more space. So 3/4 to 4/5. Okay. And now we'll do it really fast. These things are here. Highlighter. Let's go. And maybe the benefit of seeing it a second time is then you can see how this all came together. So as we go, the 3/4, 4/5 add together, 7/9. Okay. And as we keep going, the next one is 3 plus 7 is 10, over 4 plus 9 is 13, 7 plus 4 is 11, divided by 9 plus 5 is 14. Let's keep going. So 3 plus 10 is 13, over 17. This is 17 over 22. And this is 18 over 23. And this is 15 over 19. Okay, and now let's finish up where we were. So over here, this one, we were supposed to put a 16 over 21. Please correct me if I make an arithmetic mistake, because that's something I'm liable to do. And we already saw the other ones are too big, all the way too big, until this last one, if we want to check. This was 15 plus 4 is 19, divided by 19 plus 5 is 24. Okay, and by the way, each of these is actually okay. Each of these happens to add up to less than 45. How about all the ones in the middle? Let's double check. What's the worst offender? Well, 45 divided by 2 is like 22.5. So as I look at these, I don't see anyone who's in danger of being over 22.5, with the possible exception of this one. But this one adds to 43. Is there another one that goes in before? What would go here? This would be 19 over 25. Oh, does that work? Let's see. 19 plus 25 is actually okay. 19 plus 25 is going to be, what is that? 44? Oh, that one's okay, close. 44, it's okay. How about over here? Over here in between, it's going to be 23 divided by 29, too big. So it looks like the answer is how many of the fractions will work. Well, and if I took one more, I'd clearly be too big, because I stop as soon as I get the sum being 45 or more. So it looks like the answer is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that the answer? I saw some people write 7 in the chat, so I'm not entirely sure. But I'm getting 10. So now I don't know what the real answer is. I don't know if the moderators are here. I do have an answer key, so let's double check. Where's the answer key? So this happens to be junior division guts round. Where are the answers? So no, those aren't answers. Those are problems. Senior answers. Junior division guts round. And what problem are we working on? Oh no, what problem was this? This was problem number 23. So what do we have? Oh my gosh, it's 10. It says it's 10. So 23, the answer is actually 10. So this worked. So it's legit. So what you just saw is that somehow this is actually a very hard problem. But I wanted to share with you, there's some really interesting math that's behind it. This is called the Fairy sequences. If you're curious at all about this, this shows that there's a lot more to math than what you might have thought of just like, solving some algebraic things. I actually think this would be very, very painful to do if you didn't know this particular tool. I don't know if the organizers expected everyone to know this particular tool, but, I guess this works. I hope that today's session was somewhat interesting to you. We today went over a whole bunch of different questions, ranging from questions that are kind of approachable to questions that are pretty hard, like what I've just done here. But my goal of doing this one was just to also open your eyes and open your mind to the fact that math is pretty beautiful. I mean, who would have thought that you could generate all the fractions in the world by doing this? It's amazing. And so if you do this, it's like, then, we saved ourselves tons of time. I didn't go and do all of the rounds in between those guys. I just zoomed into here and I said, look at that. Those are all the ones I have to worry about. Okay. Well, in that case, we've gone way over time. I will say this session, I had intended to let people ask a few questions here and there. Does anyone have any question you want to ask me? I'm happy to stick around for like 5 minutes or so, answering random questions. They can be legit questions, and they can be troll questions, but I might not answer those. Wow, this is so neat. I'm watching 2 chats at the exact same time. We are ending. Unfortunately, this was supposed to be a 1 hour session. I went a bit longer because of the snafu we had in the beginning of people not being able to join the Zoom because this was somehow too popular. Why is it called fairy? That's a good question. Because it's magical like fairies. Well, actually, probably there was somebody named Fairy. Okay, more questions. I see that some people are saying, is my Wikipedia website all right? Honestly, I don't edit my Wikipedia website, so I'm quite intrigued. I guess I'm quite tickled every time I look at it and see what random people have been writing about it. No, I don't think you should edit your own Wikipedia. I think that's just wrong. I think if you have to, I mean, not if you have to, but I think it's best if you actually have a Wikipedia page that is what other people think of you, as opposed to what you decided to say about yourself. I already have my own website that says what I think. The Wikipedia is for other people. CJ says, this is the first time I found this YouTube channel. Well, it is a YouTube channel, although in recent days, we haven't been putting as many things to it because I've been a little busy with other things. But on this YouTube channel, you will see my random escapades doing various kinds of math teaching, such as my university class at Carnegie Mellon. More questions. People ask what's my favorite math subject, right? So my favorite math subject is neat stuff. And that's how I picked the questions to talk about today. You see, there were all these questions. This thing was so big. They gave me so many questions to look at. And they're beautiful. The fact that these students went through the effort to make so many questions is amazing. But unfortunately, I can't talk about all of them. And so what I chose to do is I chose to just talk about the ones that I thought I could tell you the best stories about. And so for me, I'm attracted to math where it's just like a neat fact, like the fairy sequence that I just shared with you. And there's no particular branch of math that I think has more beautiful, neat things than any other. Somebody asked, why did you decide to be the national IMO coach? Well, so honestly, it's because I was asked, and I guess I'd always wanted to help give back by teaching people. And so when I was given that opportunity, I said this would be great. And I then used that to just start running around the country and the world giving math talks. Because of COVID, I haven't been able to do that for a while. But I would say the thing that I love the most about being the national IMO coach is getting to meet many of you. I actually got to meet the organizer of Cowconuts, Mason, in San Francisco area once. More questions. You want to know more stuff I use for the computer background and stuff. Honestly, you guys are pretty tech savvy, I'm pretty sure. So you could probably try to figure out how I do all of these things. It's not really rocket science. I just use a program called OBS Studio, and then use your own creativity after that. Jigs, green shirt is back. Somebody said they're guessing I'm using a green screen. Good guess. I think that given the fact that on the YouTube channel they're saying that I should go and wear a green shirt, that sort of gives away that there is a green screen here. But I like to be able to teach in a way where you can see me pointing at things. I think that's actually part of the teaching. Somebody asked, what is my favorite color? I've actually answered that one before in one of my live streams. It's this color, this ambiguous color, which is somewhere between blue and purple. I like that one because it's hard to tell whether it's blue or whether it's purple. I remember we even gave a name to it. The name we gave to it was Blurple. So my favorite color is Blurple. And somebody says they don't see the green screen. That's because the way this is working is if there's a green screen, a green colored screen, then it can get replaced by any color you like. And this is the color I like. Blurple. Okay. Can you show us a cool background? To be honest, this is my cool background, this one. I like this one because of the color. The hue is very nice. Do I have any siblings? Oh yes. I'm surprised my Wikipedia article doesn't say. So I have two other siblings, Po-Shen Loh and Po-Ling Loh, and they both do math and its applications. So I grew up with them, and so I think that influenced my own way of learning math as well. What do my siblings think about me? I think you'll have to ask them. I think the best thing is to ask other people what they think as opposed to me telling you what they think. People are asking me what's my favorite number. I think I don't know. I mean, lots of numbers are really nice. Maybe I'll put my favorite number at E because E is unappreciated, underappreciated. E is this number like 2.71828-ish. And most people say like pi or I, but I'm going to put E. E is really special. Okay. What did I think of the average difficulties of the junior and senior rounds for the contest? Well, as you can see, I picked out some interesting questions from the junior guts round. So I actually found that the junior round had some fairly challenging questions, and the senior round also had some of the questions which were not as challenging, but I think that's good. I think it's good. Rickroll everyone with your background. Do you give tours? Do you mean at Carnegie Mellon University? So actually, during the pre-COVID times, I would actually, when students are visiting, I would sometimes give part of the presentation for the mathematics department's welcome session. So you would see me there. Although right now, because of the COVID situation, we're not able to do that. Wow, somebody asked, what's your favorite very large number? I'm not sure I have one. And the reason is because the numbers just tend to get large. There's a lot of very large numbers out there. So it's hard for me to say which one. You see, for me, the reason why I like E is because there's some very fundamental thing about it. But there aren't that many very large numbers that are extraordinarily, like, fundamentally important. What do you think about formulas? I think formulas are not really good to memorize unless you understand exactly where they come from. Because if you're trying to memorize, you can forget. And if you forget, you're like, oh no, how exactly was this? And if you don't know how to get it back, then the formula is useless. So to me, I think it's best to kind of not remember how to do things, but figure things out as you go. I see that somebody has asked, are you part of MOP as well? I guess. I mean, I was a MOP student way back in the day, and nowadays I'm involved in organizing it. So I guess I'm part of MOP as well. I see that there's very, very many interesting questions that are coming here. I see that on the Zoom, people are talking about I, which is the imaginary number. And, oh yes, somebody else is saying you can edit the Wikipedia page. So, yeah, you can. Sure you can. I don't think that there's a rule that says only certain people are allowed to edit a page. I would request that if you do it, please do it correctly. That's all we care about. I see. And I also saw somebody saying something about the Boink theorem, right? I think that, you see, I think of a lot of things as interesting relationships. And so in my head, I don't care what the theorem is called. It's just a certain relationship. And in my head, that relationship is Boink because it's somehow going Boink. I see that somebody has asked, why is this named Cowconuts? I don't know. I know what coconuts are, but I don't know what Cowconuts are. So I think that would be for the organizers to answer that question. Maybe they can tell you someday. Somebody says it's cows plus coconuts, or coconuts made by cows. I'm not entirely sure, but I think that they are quite creative people. Mooconuts, apparently. Okay, let me use the last one. I'm going to close out the session. I'm going to answer one last question. Looks like a neat question, saying that some problems can be solved by computer programs. How can we strike a balance between learning math and programming? I think you should do both. When I say strike a balance, I think it's really good to know math, and it's also really good to know how to program. If you can do both of them at the same time, then someday, if you come up with a crazy idea that you want to turn into reality, you don't have to go and find someone else to program it. As some of you know, that's actually what I've been spending most of my time on these days with an app called Novid to try to stop the spread of COVID-19, right? But the point is, if you have learned both how to do math and also how to program, someday when you have an idea, you can actually be involved in turning the idea into reality. So when I was in high school, I actually spent a lot of time doing math contests like this Cowconuts. And I also spent a lot of time writing my own programs just to see if I could write a program to make a video game, or to compute something for me, or to help me take a tedious task and make it simple. So I would recommend that you do split your time between the two, and also other subjects. It's good to learn about science, good to learn about history. It's good to learn about lots of things. And that might be why also the way I like to run all of these live streams is I end up sort of talking about lots of different topics in the same live stream. So hopefully today you got to see a lot of different topics where we even bounced all the way out into these like fairy sequences. Somebody asked how to reach me if you have more questions. Do I have WeChat for you to add? These days, I personally am not as active on all of the messaging platforms. But if you do want to stay in touch, we send a newsletter out every about 2 weeks, I think. And so if you go to the link to register for our newsletter, then you can keep up with whatever crazy things are going on. If you have particular questions, I do want to get back into live streams again whenever I get the time. Oh, somebody asked, where is the newsletter? The way to find that is you should just go to this main website for all the live streams I run. That main website is called poshenloh.com/live. It's just my name, smashed together, poshenloh.com/live. Or if you just go to my website, poshenloh.com, you can click on something that goes to the live stream page. And there's a button at the very top of that live stream page that says, join mailing list. That's the best way to stay in touch with myself and our team, which is always thinking of what to do with mathematics in these crazy times when, in some sense, many of us are also learning independently. So the best way to get in touch with me is kind of go through those general contacts, which are on my main website. And if you have particular questions, if you show up for these kinds of events, I do usually like to have a Q&A part where I can answer random questions people have. Okay. Well, with that, I'm sorry, I have to actually go and close out for today because I also have to go back to the other things that I work on. But it was a real pleasure to work with all of you. Let's give a big thank you to the Cowconuts team, led by Mason, I believe. Let's give him a big shout out. Right, this was good. That was my clap. I'm sorry, I don't have like 50 million claps in a clap stream. But really, thank you to the organizers. Thank you for putting so much hard work into this. You made some really neat questions. I enjoyed them. And so with that, I'm going to say thank you to all and have a great evening. When I close out the Zoom room, the whole thing will close, and so everyone will go out. The YouTube chat is actually still going for a little while. I'll probably close that in a few minutes too. But thank you to everyone, and I'll see you again another time. Bye-bye.